Well, this week we are going to focus more on basically vibrations. As you know, in the initial lectures I had told you, in machinery condition monitoring, 70% of the troubleshooting or the fault identification is actually done by monitoring the vibrations produced by these machines. Well, vibrations, as you know, is almost a 40-hour lecture in any undergraduate curriculum in an institute. But we are going to give you the basics in about a week's time, about 2 to 3 hours of lectures, and we will be demonstrating to you and showing you how vibrations is useful for machinery condition monitoring. As you know, vibration deals with the oscillatory motion of any system. Okay. So, when I before I go into the vibrations, I will give you certain basic definitions or ideas. For example, if when I say a body, this body is in space, this body could be small, big, it is a material, but if this body is predominantly made to have motions, rectilinear motion in x, y, z directions which are independent, and rotations about x, y, z, I will have this body has 6 independent directions of motion. And each such direction is known as a degree of freedom. So, vibration definitely comes with a direction. So, vibration is a vector quantity. So, it has both magnitude and also phase. So, we will consider vibration in many times as to whether we will have a body where we can divide into many small masses. So, this division is up to us. So, I can have theoretically infinite degrees of freedom in which this body will have motion, but it is this motion of this body which is about a mean position. If you think of a pendulum, this is its mean position, but then this pendulum will oscillate and it will have a to and fro motion. So, this is nothing but this pendulum is supposed to have an oscillatory motion. So, all bodies possessing mass and elasticity are capable of relative motion. The vibrating system may be in the form of a structure, machine, component, or a group of machines, right. But vibrations can be objectional, that is, it causes failure by fatigue, etc. And sometimes we use vibrations for our help. Vibrations are desirable. What are they? Desirable vibrations. Many practical examples are there. For example, ultrasonic cleaning of components. Okay. Jackhammering. Etc. Of course, the most important thing in terms of condition monitoring is response of a machine. In order to diagnose faults. Okay. But then there is a lot of undesirable vibrations, as in vibration will cause fatigue failure, will create human discomfort, and so on. We will discuss this in one of the later classes and show you examples, practical examples, where vibration is undesirable and vibration is desirable. But in machinery condition monitoring, we have a transducer on a machine and we get this vibration signal Vt, something like this. So, it is by analyzing this signal, which we will discuss the techniques of analysis later on, we can find out what is the faults in the machine. Okay. But one thing I must tell you, when I draw a body, if I consider this to be rigid, okay, so all the motion is about its center of mass. So, I can relate the vibration of the body or the motion of the body about its center of mass. Okay. But no body in reality is rigid. They can be, they are elastic because they have Young's modulus, mass, they have stiffness, etc. So, an elastic body or body which will deform will have infinite degrees of freedom. For the sake of understanding, we will be right now considering the rigid body vibration of a body of mass m about its center of mass. So, why vibration is important? As I was mentioning, vibration can cause discomfort, injuries in humans during the use of hand-arm vibration equipment. You must have seen people holding jackhammering equipment to break concrete, etc. at their hands. They will be exposed to high levels of vibrations and they may have a nervous disorder. Vibrations can cause fatigue in products and then they may break or fail. Obviously, vibrations in a structure cause noise. I have a panel like a car body panel. If there is some force, there will be vibrations of the surface and this vibration is going to radiate noise. So, vibration will radiate noise, and I am sure all of you would have experienced this. Any panel, etc., or in fact any matter which vibrates will generate certain noise, because what happens if this surface has a motion, you can imagine the air molecules next to the surface will also have the same motion, and once the air molecules are in motion, they will generate a wave. Okay, and this happens all throughout. So, vibrations generate noise. In fact, in many of the noise control approaches, you will see people reduce the vibrations to control noise. A lot of application of these vibrations in structural dynamics, to understand the dynamic loading at resonance, to know the system's sustainability in vibration environment, fatigue analysis, and of course, lastly, which is important for us, is to know the condition of the machine components because of the vibration it is producing. Now, let me take the case of a single degree of freedom system, where this is a body, rigid body of mass m. It is only allowed to move in this x direction as shown here. So, basically, though if it was in space, it could have moved in 6 degrees of freedom, but I am only constraining the remaining 5 and allowing it to move in the vertical direction. So, this is suspended by a spring of stiffness k and a damper of coefficient c. So, if I write the, and then it is subjected to an external force, or in many times I will just give an initial perturbation to this mass and see the motion x. So, this we will now study what this motion x looks like. So, if you look at the free body diagram of this body, there is a resultant force and then there is a of course, the the body weight has not been shown because it has been balanced by the static deflection. So, the net force will be shown this way, wherein the net acceleration of the body is given by this expression, where F is the external force. Okay. So, I have m x double dot plus c x dot plus k x is equal to f t is the equation of this motion. Now, there can be many solutions to this equation, differential equation, and this is the first order linear differential equation. So, x is equal to a sin omega t can be a solution to this expression, and if I substitute x dot is equal to a omega cosine omega t and x double dot is equal to minus a omega sin omega t in the above equation, I will come up with an expression where omega n is equal to root over k by m, and which is known as the natural frequency of the system. This is the circular natural frequency, where f n is equal to nothing but omega n by 2 pi. And usually the units is radians per second, and for f n the units is cycles per second, or it is written as HERTZ or capital H small z. So, this is the natural frequency of this body, rigid body of mass m, and so on. There is an expression called damping ratio. It is given by C by root over 2 k m. Okay. We will see certain cases when initially for the case of free vibration there is no force. So, f t becomes 0, and we have certain initial displacement x naught and v naught. Okay. And then we will see the solutions to this in the later. But then if I give an harmonic excitation, why is it called harmonic? Where because the external force is a function of this sin omega t or cosine omega t. So, this becomes the equation of the motion to the system. So, equation 2 will have two solutions, two parts to the solutions. One is the complementary function, another is the particular integral. So, the complementary function satisfies this homogeneous equation when the right hand side is equal to 0. So, we can find out the solution where x c is equal to c e to the power s t, where c and s are constants, and if you plug it in, we will get the complementary solution like this: c 1 e to the power minus zeta omega n plus zeta square minus 1 omega n t, and so on, where c 1 and c 2 will depend on the initial conditions x naught and v naught, and thus we can find out the solution, complementary function solution to this differential equation. Okay. So, in the free vibration case, at t is equal to 0, we will give there is no excitation or disturbance, and there will be few cases when we have zeta equal to 0, undamped case, because damping does not exist. So, this could be one solution, and then underdamped case, critically damped and overdamped case. We will see the plot of these responses of this body to this kind of damping scenarios. So, this is the free vibration of a body of mass 1 kilogram, stiffness k is equal to 1000 Newton per meter, initial displacement x naught as 0.02 meter, v naught initial velocity as 0, and these are the plots for few different cases of zeta. So, we will see the case of an undamped motion, the black line, you will see the oscillations do not die with time and they are perpetually existing. Well, reality this does not happen, because there is inherent material damping in every body, and in fact the joints in the systems etc. give damping. So, this will reduce, and for the underdamped case zeta is equal to 0.02, you will see the blue curve and so on, and just for the critical damped case or the overdamped case, there is hardly any oscillatory motion. So, usually in practice we will see many of the vibrations response which we will measure will follow the curve of free vibration will follow the curve of the underdamped case when zeta is equal to 0.02 or some other value of zeta which is less than 1. Okay. And this is for the case of a free vibration. By the way, in machinery condition monitoring, you will see because of a defect there is always a force onto the body. So, the force could be something like F0 sin omega t, where omega is the external forcing frequency. Okay. So, we will see this response will actually be at a frequency equal to omega, but this body has certain stiffness and mass. So, it has a natural frequency. When the external frequency omega is equal to omega n, we will have a condition of resonance, and this has to be avoided at all. We will continue the discussion to the force vibration for the particular integral solution. So, I can have a response like this B 1 sin omega t plus B 2 cosine omega t. If I substitute this, I will have the particular integral in this form given by a phase. Phase is nothing but the response between the forcing function, the phase difference between the response and the forcing function. So, in non-dimensionalized term, this is very important, that x by x naught is given by 1 by 1 minus r square root plus 2 zeta r whole square. Okay. Where r is equal to omega by omega n and zeta is equal to c by 2 root over k times m, and omega n is equal to root over k by m. Okay. So, this response, as you will see, you will see this is the dynamic magnification factor as a function of damping and frequency response. When we have frequency ratio r as 1, that is omega by omega n, for the case of very less damping or no damping, this almost peaks to an infinite, but with damping the peaks reduce. So, we will see that the vibration response at resonance can be controlled by increasing damping. Now, this is one takeaway we have from the slide, and you will see for the case of no damping, okay, the phase angle changes by 90 degrees here, okay, and this is a function of the increasing damping. So, change in the phase angle between the response and the force and the maximum value of the response at frequency ratio 1, okay, are indicators by which we can find out the occurrence of a natural frequency and so on. Okay. So, many systems we need to find out the natural frequency of systems. So, looking at the phase phase response between or phase angle between response and phase and force, we can find out the natural frequency. Now, we would have seen this was for a single system, but many systems you will see that there is an input and there is an output, or this could have been a force and this could have been a response, and this could have been my machine or a system. Excuse me. So, there are certain names given to these ratios. Okay. The ratio could be in the form of x omega, which is nothing but displacement, or x dot omega, which is nothing but velocity, or x double dot omega, which is nothing but acceleration, and this is an input force x. So, there are certain in a linear system certain names given to these ratios, which are known as transfer function in the frequency domain. Compliance is nothing but the displacement by the force, and inverse of this is the dynamic stiffness. Similarly, mobility is nothing but the velocity by the force, and inverse of that is the mechanical impedance, and acceleration is nothing but the acceleration by force, and the inverse is either the dynamic mass or the apparent mass. So, these transfer functions helps us characterize the system, okay, and there is and we can find out the mechanical impedance of many different elements like spring, damper or mass, and you can see the corresponding phase. So, this is like an homework for all of you to find out the impedances of few mechanical systems like a spring, damper and mass, and I had just shown you what this impedance value is. So, you can give an force, harmonic force, find out the displacement, find out the velocity, and take the ratio to find out the impedance. Now, sometimes in vibrations the magnitude and phase are plotted together as a function of frequency, and such is known as the bode plot. Now, when I say here magnitude dB, basically this is a log scale. So, if it is logarithm of any number when it is 1 to any base is actually 0. Okay. So, when this ratio output by input becomes 1, when output is equal to input, this is what is represented by 0 decibels. So, when I say magnitude here, it is 10 log 10 okay, of the transfer function. So, bode plot is used to describe the system's response. So, I can see here that this is a resonance, phase angle has undergone a change, and there is a peak at a particular frequency ratio. So, I can or frequency, and so I can find out what is the natural frequency of the system. So, this is what is known as a bode plot, and we will be using this to find out the natural frequency of the system. Of course, I shown you impedance and mobility. Sometimes to know more about the systems, there is a technique called experimental modal analysis. We will be discussing this later towards the end of this course, but just to give an example, here we have a plate and a transducer is put to measure its response. This is an exciter, or I could have an impact hammer with a force transducer. So, simultaneously I can know what is the force being applied to the system and the response generated. So, then I can find out the impedance of the system or the mobility of the system and plot it as a bode plot to find out the natural frequency. So, in fact, if you look at the system, this system has many degrees of freedom, and right now we have just shown you the two natural frequencies of a clamped plate, and this is the coherence which I will describe you later on as the causality between the input and the output. Okay. And this means the force is only producing the response and so on at almost all the frequencies. Through finite element studies, people have done this in the sense we have divided a plate into many bodies and then done a finite element study to find out the natural frequencies of this cantilever plate or beam. Now, we have some idea regarding stiffness, mass of a system, but then as you would have seen, this damping controls the response, vibration response of many of the systems. So, mostly vibration is undesirable and interest lies in reducing it by damping. You would have seen the case of the the dynamic magnification factor, where by reducing the damping we could play around. So, but then there are many models of damping. One is the viscous damping, where it is a linear combination of mass and stiffness matrix. We have hysteric damping, usually in the structures, or the dry friction or Coulomb damping given by this expression. So, different models of damping can be used to describe your model and many a times in materials there is a lot of internal damping, structural damping at interfaces and joints, and fluid damping through fluid structures and interactions. So, these dampings control the response and we must have a good idea of estimation of the dampings in the system. The hysteric loop because of mechanical damping. So, metallurgists are developing materials with high damping capacity, so that the vibrations could be reduced, like the cylinder block of an engine having materials made of materials having high damping and so on. And then for viscous elastic damping, there are different models which we will refer to in many advanced books on damping and so on. Damping can be measured either through time response measurements or through frequency response measurements, and this is the log decrement method. If you recall, in the case of the underdamped case, because of damping presence, these oscillations will die out with time. So, by measuring the successive amplitude ratios, one can get the estimate of the damping present in a system, and that is usually used by many experimenters to find out the damping in systems. There is another method which is known as the half power method. In the frequency domain, looking at resonance, if the peakness or the sharpness of this peak depends on the damping present in the system, and this is calculated by what is known as the loss factor of the system, and omega 1, omega 2 are points where this amplitude has reduced by root 2, or that is 0.707 q. So, we can find out these two resonances points omega 2, omega 1, where delta omega is omega 2 minus omega 1 and omega r is the resonant frequency, and at every natural frequency we can find out the damping in a system. There is an ASTM standard to measure damping, okay, and this could be put in a chamber with an exciter and a response, and there are equipment like dynamic mechanical analyzer, wherein you can find out damping in the material for different temperatures, and this is an experiment in the lab wherein we are exciting and we have a response to find out the damping in a cantilever beam. Certain parameters are used, you will see in the literature. We have used this as damping ratio, somebody calls them 2 eta as loss factor, quality factor as 1 by eta, okay, 2 zeta and 1 by eta, and damping capacity is quality factor by pi and so on. Okay. So, these are all related terms which you will find in the literature. More examples and applications you will find in my resources. Thank you.